Well, Don, thank you very much for doing this with us and for bringing over these materials. Is it correct that these represent some of the very first computer programs that you worked on?
I think I have the first large, with me I have the first large program I ever wrote, which would have been 1957, so what's that, 61 years ago. And it was in June of 57. It was a program to play Tic-Tac-Toe. And my very first program was to find prime factors of a number that you dialed in the console of the machine. And I should have looked for it because I'm pretty sure I have that somewhere, but I didn't think about bringing it. And the second program was a program to do radix conversion. But those were real short, things. I think the prime number program, by the time I finished it, I think it was like 40 lines of code, and I had to remove 60 bugs or something. But I added bells and whistles to make it run a little faster, and then I'd find that some numbers had so many factors that I had to punch 2 cards instead of 1, and things like this. But anyway, that was my first. Prime factors was my first program, and that's when I discovered debugging, and I worked real hard on that, and then I got the other one going, and then I said, wouldn't it be fun to play a game? And on the 650 we had only 2,000 words of memory, and the word was 10 digits. So a word was what is it? A digit is 4 bits, and so we get we get 11 bits in our words. I'm sorry, 41 bits in our words, because there was a sign. So you had 10 digits and a sign, and 2,000 of those on a drum. And so, but I wanted to play tic-tac-toe in an interesting way. I wanted the machine to learn. So I built 3 programs. I wrote a program that would have the general interface for playing tic-tac-toe, and then I had what I called Brain 1, Brain 2, and Brain 3, which were used on the other side of. So the user interface was the same, but I could change the brain that the user was playing against, and Brain 1 it was pre-programmed with the way that I that I knew was good. What was Brain 2? Anyway, Brain 3 was the one that learned. I guess Brain 2 it would just play at random, but it would remember past games, and every move that had occurred during a previous game that had ended up in a loss or win or loss, it would say this position is good for this player but not good for this player, and if it was a draw, it would sort of move the rating towards neutral, and it would play against and so then Brain 3 was the way that I could hook up Brain 2 playing against Brain 1, or Brain 2 playing against Brain 2, or Brain 1 playing against Brain 1, and things like that. I could have the computer playing itself in different ways. So anyway, that was the first big program that I wrote, because in order to...
Is that with you
it's
here?
Yeah.
Could you show it to us?
Yeah, I will. So, let's see. Yeah. I hope I have it. I hope I have it here. Let's see. No, this is not it. Here it is. Okay. Yeah. Okay. Tic-Tac-Toe program and example games. My first large-scale computer program, summer of 1957. Okay.
And could you describe to us is this, pardon me, it's hard for me to see, but
Yeah.
is it what is it in machine language, or is
This is in assembler,
an assembler?
and it must be SOAP 2 or SOAP 1 maybe, if I wrote it in 1957. It was the first assembly program for the 650. It came from, but I wrote my own assembler as I'll point out later. But
That would be the SuperSOAP,
well,
the one that you created.
several others, yeah.
Okay.
Right, and so then so this is just a listing. The cards are, I believe, are long gone. It's not impossible that they do exist somewhere in some box, but and you can see the ribbon was filled into zeros, and you can't tell a zero from an O on this printer, but you're never going to have an O in the numeric column, and you're never going to have a zero in the NOP instruction, the no-op instruction. So you can tell by context, all right, except when I have a symbol. And so what do I put here? I didn't know that. I stuck this. I stuck this in about a. It's a commentary. IEEE supplement to volume 103, 1956, discussion about computer playing tic-tac-toe by Dave Davies and Robert Fairthorne of England. Okay, so
Well,
I didn't know I had this in here, but that sheet is stuck in here. Okay, so the first thing, I don't remember how to do it. I call this the gaily colored pack. So you had to put you had to put the cards in different ways depending on how you're running the program. So I had different colors of them in order to describe. So it'll take a bit of figuring out what it does, but I think I spent 4 to 6 weeks on this program, and it's very hard to fit it into the 2,000 locations because the number of different positions possible in tic-tac-toe is rather large. If you don't do anything fancy, you've got 3 possibilities for each of 9 positions. So you have 3 to the 9th things already there. X, O, or blank in each of 9 positions. And so, what is 3 to the 9th? That's 9. That's 27 cubed. So anyway, it's less than. I should know 3 to the 9. Let's see, 27. Let's take 30 cubed is easy. That's 27,000, right? And so it's up there. So I also had to divide by 8, considering the symmetries of the board, and I also had to pack into words. And the 650 had these very strange instructions which were intended to read sensory data, somehow magnetic brushes. Anyway, there was a strange instruction that would branch on whether you had an 8 or 9 in a bit position, in a digit position. And you could, so so anyway, I had 1 digit position for every possible position in tic-tac-toe, and I could encode a number from 0 to 9, and 9 was, say, very desirable position. 0 was a very bad position, and 4 was the initial condition, something like that. All right, And so that was my machine learning mechanism. No neural network here, but it was actually trained.
Well, it is interesting that today there's so much discussion of having these machines play themselves.
Oh, yeah.
And it's
Well, here it is.
Yeah.
And so Brain 1. I remember the joy I felt when I was writing this program, because you have to describe yourself in 5-letter words. In this assembler, you can give symbolic names, but it has to be 5 letters. You don't have 6 letters or anything like that. It's all fixed format. And so one of my is brain, okay? And, I have skip and error. But I remember the great joy that I felt when I invented the name that I would use for when somebody scored a win in Tic-Tac-Toe, and I called it bingo. And so there'll be somewhere in here there'll be a place where you go to bingo, and that was my great joy to be able to say that in this program. Okay, now so there's Brain 1, Brain 2, and Brain 3, and there are and then at the end I have Brain 3. No, so Brain 3 was the learner. So Brain 1 and 2 must have been something about random or expert or something like that. And so here, July 22nd, 1957. So I ran into July, started in June, and so here are some of the games that the first. This is a blind, a blind person playing against a blind person. None of they're moving. All moves look the same to them, and so he plays the one here. He plays next to it. He put the one there. He put the one here. This guy won. Okay, so next time he goes somewhere else. Okay, all right. And so at the beginning, they stumble on a victory. They don't even know. You have a win in one, but you don't see it until you learn more. But eventually, it got really dull because they just played safe. Okay. Oh, then I had 817 games. The first moves of Brain 3B were predetermined. So it says here 36.8 seconds per game.
So this was two trained Brain 3s competing?
So Brain 3 is changing its memory as to how desirable moves are. I don't know what this is a printout of the something in the memory. I'm not sure what it was. The earlier programs will, of course, tell you the format in which these other ones are. Somebody wants to have instruction reading code, learning how to read code, and we got this guy in Spain that can run this program now, and so he figured out what it was. So this was what I cut my teeth on before I wrote any software for anybody else. The rest of the summer I spent writing, reading the compiler that had been written at Carnegie, the IT compiler, the Perlis Van Zoren Smith compiler, and I read the source code of SOAP 2.
Which was SOAP 2 was?
SOAP 2 was from IBM. This was Stan Poley. And it was the first beautiful program I ever read. Perlis's program was ugly and awful, but Poley's program was was a delight. It was like a symphony.
Could you, for someone who hasn't had that experience of reading source code and seeing, beauty or ugliness, how would you explain it to somebody? What the sorts of things that you saw that were evoking those?
Well, it's like, by the way, I tried to describe it in print. I wrote this. There was a special issue for the Annals, History of Computing, special issue for the 650. That was about 30 years ago or something like that. And I don't know, maybe. Oh gosh, I think it was IBM super salesman, the guy who lived in Portola Valley and was an expert on, let's see now, what name? Gosh, so he's one of the world authorities on manzanitas. Yeah, that might help me remember his name. Manzanita. Calvin Clayton. It started with a C. Okay, so he was the guy who went around selling IBM 704s to people, and in the 50s, and then became a vice president of IBM and very famous person. And I think he commissioned this special issue on the 650, and I wrote it. And my memoir to the 650 was something like the IBM 650, an appreciation from the field. And IBM terminology, the field was outside of Armonk, and so in there I explained, I think, about some of the joy I had of programming at the time. But anyway, not to duck the question, but I was okay. So it was between my freshman and sophomore year. I came to Case, and in December of my freshman year, Case got a 650 as a present from IBM, a loan. It was leased from IBM and installed for the campus, and I got fascinated by it, and I learned about programming it a little bit. But then I had a summer job starting in June to work at the computer lab, and Case was very unusual that they trusted undergraduates to actually touch computers. At Stanford, computers were expensive. You would have professionals doing it, and people would. You could touch the key punches and submit your jobs at some window, and then come back the next day and get the answer. But at Case, we were allowed to touch the machines, stay up all night with them, write software for the machines, and I was even able to to write the user manual for the compiler that I wrote. Several of us worked together on the compiler, but I wrote the manual, and then this manual was published by Computing Center, and I wrote it when I was a sophomore, and it was a textbook in my class when I was a junior. So I had this lovely thing that I had able to write one of my own textbooks. Okay, so this copy that I'm lending to you has my wife's maiden name on it. So she took a class from this book, and we had some tearful nights as we're understanding it. But this would be her handwriting here, as she's trying to understand the compiler that I wrote. And here's my writing of the compiler here. So anyway, that was this was public. This was a more polished compiler that we finished during the summer of '58. So my sophomore year, between my sophomore and junior year, we completed this compiler for the 650, and it was really much better than any other compiler for the 650. And there was the one at Carnegie, the IT, but this one did all that. It was upward compatible, but it had many more things that you could do. You know, two-dimensional arrays instead of one-dimensional, et cetera, et cetera. And then there was another compiler written at Michigan, but anyway, this one was quite special, and it was because they let us undergraduates write it, and one of the besides myself, one of the main contributors was Bill Lynch, who you know. I mean, I don't know if he's a trustee of the museum or something, but he's active in museum activity. Okay, so Bill and I did a lot of the coding for this, and he was 1 year ahead of me.
And this was after you had that reading your first beautiful program, which was the SOAP compiler.
Right. So okay. So here I am. I see this. I see this machine, and I learn that this machine has a strange piece of software on it called compiler, and it blew my mind. The compiler would understand algebra. You could write left parenthesis, A plus B, right parenthesis divided by C plus, and another parenthesis and so on, just like we did in the algebra book, and it would convert that into machine language. Yeah, I mean, it would sit there and it would speak, and the lights would flash for about 10 seconds, and that would punch, and those cards were actually doing that formula. And I couldn't believe that. I thought it. I'd figured out how to play tic-tac-toe, but I hadn't the slightest idea how anybody would be able to do that with parenthesis and algebra formula. That was a different world to me. And how could it be? And so at the beginning of July or so, we received from Carnegie the report about the internal translator, but it included the listing. So it's this long report. You must have a copy. I mean, I didn't bring it with me because I figured that that's something the museum must already have. And similarly, I have the SOAP 2 programming manual, which I read a month later, which came from IBM, and that's well known. If you don't have it, I have a copy. But anyway, so this program, I have a lot of relatives around Cleveland where and they traditionally rent a summer cottage for a couple of weeks on Lake Erie. So we went there to summer cottage, and I spent all the time looking at Perlis's program and line by line figuring out reverse engineering the program. How the heck does it work? And so at the end of those 2 weeks, I knew how it worked, and I also knew that it was very ugly programming because because they would do things in 5 instructions that I could do in 2. And they would repeat things. They would set something to 1, but it was already 1. They didn't know what they were doing. They were working with a committee basically, probably, they started out with this idea that they were going to design the whole assembler based on a big branch. For every pair of characters that could be next to each other, it jumped to a special code for that thing. So if you have a plus sign followed by a letter X, then you go to a certain place which handled that. And it was spaghetti code, but you could eventually figure out there was a system to it. But of course we found bugs in it too. But that's the way it is with spaghetti code. Okay, so but at least I knew it was possible. I had this existence theorem. Yes, a compiler can be written, and then. It was written in SOAP 1, I think. Anyway, it was written in assembler language. But then I saw SOAP 2, which came out, which was a much more elegant design of the assembler for the 650. And I looked at Stan Poley's code, and here he would do in one instruction what normally you'd think would take three. I mean, when he would load the lower accumulator, he would also know that he was putting something in the data slot of the distributor, which he could then store and use for some other purpose. And so he was fluent with the thing, and so it's like seeing a good piece of machinery where things gel and fit together, and others where it goes clunk clunk clunk, and you have to oil it more. So that's the difference, and it. So there's many different styles that you can perceive in programming as you read them. You get to know. In fact, I'm sure that I could detect at least two programmers in this Carnegie thing. And I didn't know who was responsible for this particular peculiarities, but you can. Once you start reading code, you can recognize that there's been a change of author here, from this page to that.
So would it be in a way that you're seeing you're seeing other people, you're seeing their craft, just like if you were looking at a machinery, a piece of machinery, like if you see some simple, elegant mechanism, you're seeing kind of. You're seeing the craft and the ingenuity of the maker.
Yeah, I mean, the source code for Unix, Unix version 4 or something, is published, and you can see the way Ken Thompson wrote code, and it's just fluent. It's somebody that, and if you're a musician, you can see the way Tchaikovsky scored music, and you can see that the Debussy is completely different. Not only the way it sounds, but the way it looks. The way they did. So this is style. In programming is the same as style in poetry or music, whatever, and mechanism design, art. So okay, now in order to write this compiler, I wanted to have a good assembler. Because SOAP 2 was beautiful, but it inspired me to do lots more, and so I added many what they called pseudo-ops, which were I don't change the machine, but I have more things that the assembler can do for you automatically, and so SOAP 3 came out, and this is the manual for it, which apparently. The guy in Spain had no way to find it. He'd been looking for it. So this is the user manual for it. And I don't know. He didn't find this report either online. So this tells the. Now we couldn't just call it SOAP 3 because that would sound like IBM product. So insisted on putting the case SOAP 3 in it, and this was my handwriting. I mean, I was very, I couldn't write. You know, these are with the fonts that I did before I did with computer. It is awful, but you know, I wrote this report. This case SOAP 3 is a modified version of SOAP 2, originally written by Stan Poley. Major changes were to add 5 instruction per card output if desired, and to use program points as a greater convenience. This is what I call local symbols. Now it was an invention of Mel Conway at Case. That is, with SOAP 2, you had to make up a 5-letter word for every time you wanted to refer to a location. But with the program points, you just, well, here's an example. It says 2F, and that refers to the 2 down here. But when this says 1F here, that refers to the next F, and 1B refers to the previous one. So you didn't have to sit there with your thesaurus trying to think of new words every time you just wanted to make a local reference down the page, and I so I added that to SOAP 2, which was a big help for the programmers, and I put it into my assembler that went into art of computer programming later, and other people picked up on this later on. But okay, then the second thing is 24 new pseudo operations and error correction routines. Okay, so.
Did you do all of this on your own, or were
yeah.
you? Okay.
Yeah. Well, no. I mean, the users said, "Don, why don't you add this pseudo operation?" But I wrote all the code, but I had a lot of feedback from people saying, why doesn't it work this way? So I. Okay.
How large was the community of people writing programs at Case at this time?
I would say there were maybe 3 dozen of us. Mm-hmm. That included UNIVAC too. So we had a UNIVAC as well. So let's say 2 dozen would use the 650. I mean, as sort of on staff. But then other people would use it casually. I guess. Mm-hmm. All right. So and then we would share this with Carnegie and Michigan and so on. We had we went so we had users outside of Case, and there was a 650 at NASA in Cleveland. So it got out, but it didn't. It wasn't distributed by IBM, so it was only done by people who had somehow local ties.
Okay. And have you brought a listing for SOAP 3
yes.
with you today? Okay.
Yes. In fact, that might be one that you already had. Okay. Let me. So I brought with me 2 reports that were. I'm not sure if you can get them through Case archives, but these might be the only last 2 surviving in the world. Most of the stuff on this table is probably, if it goes, then it is lost forever. There are no backups for these, and so I hate to. I hate to imagine what would happen if you guys mess up on this.
I hate almost more to imagine that. Yeah.
Okay. But all right. So now here, I have a program that I have no idea what it does, and it says rectangular game solver, simplex method. And so it sounds to me like that this is a program that I wrote since it's dated 1959 and it's fairly short, it sounds like it's a program that I wrote after I had learned the theory of two-person, what they call zero-sum games. There was a very nice book that I read at the time. You have it's a rectangular game. In other words, the rows are played by one player and the columns are another. It's like scissors, paper, rock, where you have a payoff. If one player says, "Okay, do row something," and the other player says what column it is, and then you look there, and that's the payoff. And so this would figure out a strategy to play that game optimally. That's probably what it is. Here I have a game. Here I have a thing called Solitaire Number 1. And I don't know what this is, but it's only 3 pages long, and so one could probably figure out it might be this peg solitaire game where you try to jump all the pegs until only one peg is left. I do remember writing a program for peg solitaire that year, and I thought, and I debugged it, and I started the program running at 9 o'clock at night, and I had the machine all to myself, it didn't finish, and so I looked at it every once in a while, and it was still running, and I never did get to sleep that night. But by 6 a.m. I realized that it was probably going to be another 200 years before it actually. It was not a very efficient program, but it was a learning experience for me, and this might be that one. This might be the program that I wrote that will never run to completion. Okay, now. SOAP 3, good listing. Okay, so I had with the collection you guys already have digitized. There's a listing of the Runcible compiler. Okay. And its runtime routines, I believe, and it also has an assembler that we used for it. But this is different. So this is the SOAP 3, which preceded SuperSOAP, and here I printed out the loading routine. You needed 4 cards in order to. These 4 cards would load themselves, and then afterwards, you would get the assembler itself, and then it would punch cards that you save and put with the loading routine and run your program afterward. Okay, so this is the whole works, and it starts out and it has serial numbers on it, so I can see how many lines of code it is. There's a section called Error Correction and Restart. Tables. Okay, here it is. So 1461 lines of code, including the tables. So that's 3/4 of the memory is in is here, and then a little bit for that symbol table, and the user's identifiers and so on had to be stored. Okay, and then I have something called hand soap, and this is something where it was patches that would change SOAP 3 to do an extension where I could control exactly where the instructions would go on the spinning drum of the machine. When we wrote software that was going to be used over and over again, like a floating point subroutine, calculated for a logarithm or something like that, we would work by hand and spend several days displacing the instructions so that the machine wouldn't waste any cycles getting around to them. And then in the right hand, so I have the program for the floating point routine in assembler, but then I also punched in the right hand side saying, by the way, put this on drum band 3. And hand SOAP was my extension to SOAP 3 that did that.
I've heard other people talk in interviews about doing exactly this sort of thing, of like optimizing exactly where you're reading and writing from the drum to make things fast. Was that something that you had discovered on your own, or was this kind of a technique?
Well, the people at Bell Labs had set the model. They had the Bell interpretive system was a guy named Vasily Valantis there had I think hand optimized his code. No, there was another guy. I give credit to this other guy in my article in the Annals who had tuned it up. But that was all done. But then they would punch it all on cards and do everything by hand. And so I wanted to automate this, and so I wanted it to be easy to do it. So that was my first paper in the ACM journal. Was about how to optimize with interactive between machine and human being. And so I had so I discussed the algorithm for hand optimization in my article, and I also had some theoretical work. But anyway, this was all part of that work. That, in other words, in order to write production software for the 650, you really should hand optimize the inner loops, and I built tools to make this possible. The previous tools hadn't used automation really. They had just said, we'll find the numbers and we'll get some secretary to type in the number.
So that is kind of, if I'm following you correctly, it's almost like building on these hand SOAP extensions. It's building on kind of what you were doing here with hand SOAP, but to run kind of, but in a more algorithmic way, rather than saying, right at this particular location at the drum. It would be like, run this tool to optimize.
I have, I didn't go that, I only had 2,000 words. Okay, so I didn't go, but I did develop for example, I developed an integer programming model that people could use, so they could feed it to people in the operations research department, and and you could say, okay, now, find the optimum solution to these linear equations in integers, and that'll be the best place to put your instructions on the 650. And unfortunately, programs were too hard for the operations research. 20 years went by before they had good enough software from those people to solve it, to actually solve these models accurately. So they could give approximate solution, but to find the absolute best solution, we had to wait. And my paper also discusses that, and the people in Europe, I think, finally solved the program that I had published in ACM Journal in 1962. After 50 years, was finally solved to optimization. But I believe that the best automation is teamwork, where the computer does 99% of the stuff, and then the human being adds the extra thing which makes it really work. Because when you feed a program to a machine and say, optimize this for me, you're only feeding one instance of that program. But you know very well that you could have written that program differently, and you're doing a floating ad, but you had your choice. So you could have changed the routine a little bit, done things in a little bit different order, maybe, and instead of adding this to this or subtracting, you know that there's different options that can go, and it's really hard to present all the possible options to the machine. So if you're working with the machine and you see how the machine does, and then you say, oh, wait a minute, I see you're having a little trouble getting this guy here. Well, why don't we change the algorithm a little bit, and so that's the way I always recommended for really doing good software, not saying that the machine does everything, but that the machine helps you do the stuff that you aren't good at, and you can give the machine the global understanding that you have, and say, here. So that was the thrust of my article. Okay, now so SOAP 3 good listing, and one of the nice things is that I actually punched on the card the date, so it said August 11th, 1958. So I know, that was as we were writing Runcible. Now here's SuperSOAP, and here I got actually a nicer font. You take a look at that. I'm starting to think about a little bit about the font. And this said August 15th, 1959. So a year went by, and I got a lot of new ideas, but we also got new hardware. So our 650 got changed to a 653, and this was floating point attachment and index registers added. So no more memory, but we have the ability to we have a few more registers and floating point built-in floating point add. And we got 60 priceless new words of memory called core. This was not a drum, but this was actually random access. 60 words, random access. And so we could take 60 words out of the drum and run it up to the core, and then execute out of the core, no delay, and 50 at a time. We had 10 words in there that we could keep up there to keep track of what's going on, but locations 9,000 through 9,059 were God's new gift to 650 programmers because they were instant access. And then we had a RAMAC, which was a jukebox contraption. There were lots of layers of platters, and a arm would come in there, go chug 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 chug, and it would read one track, around 60 words on a track, and those would go up into the core memory. And so we need another assembler, because when you're writing a program, that's supposed to run out of these 9,000 instructions, you need a feature that wasn't in any of the other assemblers before. You have to, it has to say go to location 9014 for your next instruction, but you store it in location 1014 in memory. There's a different address at assembly time from address at runtime. And so I had to build in a facility that a programmer could use without getting screwed up, that would be able to write programs to take advantage of the feature. And so, and of course it's written in its own language, but I have the manual for it here, and the complete code. And the guy in Spain has a RAMAC that he's simulating. So he has a virtual 653 the way we did at that time, but he had no programs to run on it. So this will be, once you digitize this will be the first time he has a chance to to really test his simulator. So you can imagine how happy he's going to be.
Yes.
So my goodness, the 5-letter words I came up with are kind of interesting. Farce. Okay, coddle. All right. So one thing I learned from Polly was hashing. So I have locus. Okay, so pretty good 5-letter words in here. Okay, now and still more pseudo operations. And it starts out with a comment saying, locafier 3800. I don't remember what locafier meant, but it must have been one of these words that we invented in order to represent the fact that instructions live in one part of memory and are executed out of another. And so I think we might have called that a locafier, but I don't. But it must be in the manual, but I don't remember that. I do remember it was a word. Okay, so SuperSOAP dated August. Then I have a listing here called super to the n soap, where n equals 2. I guess I was thinking recursively, I don't know. And this is dated September 1959. So this was August, and this is September 3rd, 1959. So I guess couldn't turn off thinking of making it more super. And I don't know if I have a manual for this, but here's the code.
And that would have been, are we now in your junior year?
So this was just before my senior year.
Okay.
So 59. So in September, at the end of September, my senior year begins, and I'm going on to graduate school in 1960, during the summer of 60, I'm driving out to Caltech. Yeah. All right. And so this is when I'm working on it with the basketball team during the year. And the last thing I have here is a SuperSOAP test deck. SuperSOAP test deck Aleph null. And the listing doesn't have a date. But it also shows the output of the test deck. So it's an example of a run of the program, of a difficult input and output of the program.
And it's really testing, what is it that it's testing?
Well, it has to test all of my pseudo-ops, and it has to test whether or not you recognize strange cases of local symbols. And
I got it.
And I have minus signs in unusual places.
Okay.
And I believe SuperSOAP incorporated hand soap as a sort of as a standard standard feature too, because we were learning how to pack instructions into the 650. The Runcible compiler was the worst example of tricky code, I think. Maybe, I don't know how, for example, it was so tricky. Every time we changed something else would break because we had forgotten, that we were doing two things at once with much of the code. And it was 4 compilers in one. There were 2 replaceable modules. You used either the red book deck or the blue deck. The red book would give you floating point built in with the hardware. The blue deck would give you floating point simulated software. And then you could also those replaced let's say 628 instructions of the compiler, and every time I figured out how to do the one in 627 instructions, then I have to figure out a way to save an instruction out of the other one, because every instruction we save would give us a chance to add a new feature somewhere else. So that was our philosophy. We pride ourselves in being able to get things into the 650 that seemed unbelievable. And then there were two other interchangeable modules too, and that as to whether you wanted to punch cards or not, or to run or to run directly, or to go through another pass or not. And so again, those were exactly the same number of instructions. And if we had if part of our program would be to read a constant and store it somewhere, we would see if there was some other constant that would probably work, that we were using for something else, because a lot of the constants are arbitrary when you're writing a compiler. You don't have to make something. You don't have to say this is going to be 1, 2, 3. It might maybe 1, 2, 4 is just as good, and maybe that'll fit with something else that you did somewhere else, and so you save space. And space was very expensive to us. It was, and so we did everything we could.
Can I ask, in creating that Runcible compiler, was there an overall plan or approach when you started making it, or was it more iterative and kind of discovery sort of?
What we wanted was to take the compiler that Perlis and his colleagues had done and redo it right, and add as many features as we could, but we started with their shell. So we said anybody has a program that, a lot of people had invested time in coding. They had decks of cards that worked on that compiler, and so they were still acceptable to our compiler, but they would run faster, and besides, we were able to do a lot more things that weren't in that. That was our goal, and we added absolute values, something like that. I don't know, the various features, but it was not. Our code was not elegant, though. The code for SuperSOAP was elegant, but this other it just got the job done. Now, here I have a program called Integer Programming Program, and this is dated April 1960. So Ralph Gomery was famous for having written all integer programming routine. This was integer programming is later proved to be NP hard, but anyway, there was linear programming where you're allowed to use rational numbers, and then there's integer programming where the solutions had to be integers, and Gomery figured out a way that would at least that it would run in finite number of steps to solve integer programming problems, and he wrote a report about it, and it was kind of famous, and I got a copy of the report, and I implemented the algorithm. He told me later that nobody at IBM had implemented the algorithm. He had just come up with the algorithm. And but I had implemented the algorithm, and I implemented it but needed more memory than the 650 had. So I used the RAMAC for the memory. So this is not very well commented, but it does have a symbol pivot in here, which looks like a good 5-letter word, and I have a couple of handwritten corrections. On the listing, but that's my and the guy in Spain said he didn't have any programs that were that ran with the RAMAC and did anything. So this is historically maybe the first implementation of Gomery's algorithm, okay, now. This is embarrassing. It starts with line number 1553. So it might be, yeah, okay, that's the end of the SuperSOAP program.
Oh, okay.
Okay, good. Almost to the end. This is the SuperSOAP manual.
Oh, great.
Fonts are terrible, but it's assembly system for the augmented 650, and I dated August, and so it's a major revision of case SOAP 3. It requires index registers core, a disk file unit, and table lookup on equal feature, but no negative opcodes are used anywhere. So the machine with the program register signed is not handicapped. I don't remember what those were. SOAP 3 was written attempting to get as many features into 2,000 memory locations as possible. SuperSOAP was written under a different philosophy. Speed was a prime consideration, and storage space was conserved only when speed was not appreciably decreased. A factor of roughly 3 to 1 in running time over SOAP 3 has thus been obtained. Some of the pseudo-op rules have become more logical thanks to Carnegie Tech's two-pass TAS assembler. And I thank Bill Lynch and so on. And I use 100 tracks of disk for temporary storage. Wow. So I didn't have to punch cards. So you could store the program there and not have to go through cards unless you wanted to. Okay, so this is, all right, now, here's, okay, so it starts out and it says, if you were going to get any good use out of this manual, you ought to be reasonably familiar with 650 machine language. But that is all you really need to know. You don't need to be acquainted with any other assembly system. And then it explains why assembly programs are nice things, and SOAP stands for Symbolic Optimum Assembler. So it starts assuming a novice reader that okay, so that's the manual. Okay, now finally, and these are little 1-page or 2-page memos that I wrote when I was an undergraduate, and I'll go through them. But anyway, again, if you lose any of this, it's gone for all time. This is so here I have a write-ups for a modification of SOAP 3 that puts subroutines into normal form that can be used with other libraries. Okay, so then I have a time study routine. Date, 1958, June 11th. So that's very big. That's very strange, because it means that I had already been working on SOAP 3 before I told you. If I'm not, unless that date is wrong, but it's dated June 11th, and so I must have had SOAP 3, or else maybe there was an IBM SOAP 3. I don't know, because I didn't think I had done much programming by June 11th of 1958. I was, wait, 58. That's okay. 57 is when I did this. Is when I dictate. Oh, yeah, 58. No problem. All right. Yeah. Okay, then here's September 58, time study routine. Use this program with SOAP 3 or SOAP 2 output cards. Discover how long the 650 is waiting while executing your program instructions. And so it was seeing if the hardware was doing what you thought it was. Here's a 2-page memo dated January '59. Clock watch. A convenience for Runcible users when debugging. It produces a play-by-play report of the program as it's running, including all intermediate answers received. So it's kind of a tracing feature. Okay, February '59, Runcible 0. It places your program, it compiles into memory. It's a load and go compiler. We saved so much instruction that we were able to free up 600 locations inside and compile into those locations. And instead of, it was a 0-pass assembler. I mean, it was one less pass than a 1-pass compiler. So we call it a 0-pass assembler. Since Runcible 1 requires 2,000 memory locations and Runcible 0 must be cut to considerably less, a few restrictions on programs have been made. Any program that would put out less than 750 SOAP cards with Runcible can be handled except in highly unusual cases, but the running time it goes down by 25%. But you're not allowed to use the following statements: matrix notation, set error correction statements. They're apparently, we had some kind of a facility that would say if error goes, if some error occurs, back up to here, something like that. And you can't use fancy iteration statements, fancy do loops. Okay, and you didn't need iteration statements because you can program them yourself if tests. Okay, so I left that out, and I also insisted that every statement fit on one card. So this was this was the Python of 1959. Okay, here's a this is a one-line thing that says number perverter demonstration card. Prepare console as follows, and then you read in this card, and it reverts the digits of a number. And at a long time, this was a challenge. Nobody was able to figure out how to do that on one card, so I had a one-card program that did it. Finally, September 1959 is a program that is for debugging together with the core memory. So, and so these were little one-page handouts that would given to all visitors to the computer center and then distributed to a lot of people using this software. I don't have the source code for these programs, but still that shows the milieu, the kind of things that were important to us at the computer center in those days.
I guess thank you for all that. I was just thinking about, people's computers on their desks today that are probably, a million times faster than the 650 or something like that.
Oh, yeah, at least.
With Lord knows how much, I don't know how many orders of magnitude more main memory and storage. I was just wondering, like, for the sorts of, for example, developing compilers, or how does this sort of work that we've just reviewed? What do you see as remaining the same and being very different when you're in a kind of completely different hardware realm today?
Yeah, well, there are still a lot of places where tight coding helps, but like we want to compress something before we archive it, before we send it. JPEG, for example. PDF, all these things are based on elaborate compression schemes in order to save things. When you're doing gaming, you've got to pack a lot of logic into small spaces. A lot of the things that people are doing now, also, just-in-time compiling, all these other stuff. It came out of the idea that we build a virtual machine for things instead of writing one piece of software that does everything. So a lot of these things definitely survive, but the aesthetics are different. Sometimes there's still an advantage of finding a short program that'll do so well. I suppose I'm writing something for neural networks that's supposed to. There are different ways of parallelizing it that can make that'll really work if I change look very carefully at the instructions that are going on, you could talk to Ken Thompson, for example. He's taken a lot of legacy code that was written in the last 20 years and rewritten it his style, and he gets it, to work much better on the modern machines. So we have all this other equipment, but still doing things an elegant way. Sometimes pays off. Sometimes it's only for show. It's only for the joy of the. It's really nice to write a haiku sometime. But if you have more time, I said I didn't have time to write a short letter, so I had to write a long one. But. So the more you can give some kind of feedback, though, to the programmers that they can pick up on some aspect of beauty, however you want to define it, that brings out their creativity and their juices and makes them come up with joy that makes them want to do better things tomorrow and so on. If it's only a matter of looking up something that's already been done there's another kind of beauty to that, I suppose. To be able to keep things going even though you don't know how they work, but that's not my style.
Hansen, did you have any questions?
Sure, yeah. Staying on this theme of elegance and the aesthetics of writing code, would you say that in this early period, parsimony was one of the primary aesthetic values that you held?
It had to be, because otherwise you couldn't do it. One of the extreme examples of this, it never became a product, but I spent maybe 6 months on it. It was Burroughs was going to come out with a little microcomputer that was intended for banks, and it had, I don't know, it was like a 4-bit computer or something like this, and the memory was a rotating disk, and it would be, and we had a little computer that would be able to write a little bit on a disk and go around, but somehow, let's see, and that would be the customer would have that, and it would have it, and his disk would have enough to replace Burroughs accounting machines, and so you'd be able to keep ledgers, financial data on these disks, and you could use it to do your payroll, and you can write a little program for this mini computer. But we had 4,000 bytes of memory, and this very awkward system, and but they figured they could sell it real cheap, and so the customer would get a typewriter and this little unit, and then the sales engineers would write the customer wouldn't know how to program, but the sales engineer would study the guy's application, and so he'd say, oh, you got a payroll, okay, here's how many accounts you have, and you want to tab over to the column 13 and do this, and then you want to keep grand totals and subtotals, and you have some kind of backup for if you made a mistake in data entry, you can say cancel it and so on. But the salesman sells the unit to the customer would know how to write a program for this little microcomputer, and so it was a nice tiny little microcomputer. But in order to write the software for it, I had to fit it into 4,000 bytes, and that included the memory for the user's program. So basically, I had 500 bytes for input-output buffer, 500 bytes for the user program, 1,000 bytes for my interpreter, and 1,000 bytes for the virtual, 1,000 bytes to write a virtual machine for my compiler, and 1,000 bytes for the logic of the compiler. So that was, and I did that. And the compiler was called SELL, S-E-L-L, Sales Engineers Little Language. And I had elaborate manual for it, and I tested it out and so on. And I based it on real world examples from my father's business. And I had 1,024 bytes to write my compiler, and and my first draft was 1,030, and so I had to save, and I wrote this elaborate test program, and I keep track of which bytes in my compiler had actually been used, and I got to the point where I was able to fit it into 1,024 bytes, and furthermore, my test program only had used 1,023 of them, and so then I looked at it and said, well, why hadn't I tested that one? And it turned out that it could never occur, so I took it out. So I had 1 byte to spare now in case there was a bug in my program. But actually, the project wasn't killed because the hardware got better at that time. This was 1963, but because Burroughs upper management realized that this machine was selling for 1/10 the cost of the machines it replaced, and it would put eight of their sort of put 8/10 of their employees out of business nationwide, making these old mechanical machines, and so they decided not to sell cheaper machines because they'd shoot themselves in the foot. And then by the time everybody did get over mechanical, so the engineers who worked on this said, but competitors are going to think of doing these things, making cheaper accounting machines someday. What do you do then? And Burroughs said, yeah, well, we'll get ready for the time, but it's not this year. But anyway, that was the ultimate in cramming, my personal ultimate of shoehorning logic into small space. But it did teach self-discipline that I find has had spin-off in just avoiding off by one errors. Other stuff. We had the case where I wrote a sorting routine for the Cray 6600. So this was the first time I had a machine with pipeline, and the idea was to get the inner loop of a merge sort down to 17 clock ticks, because we had that's how many clock ticks we had in order not to miss a cycle on the spinning disk. And one clock tick on the 6600 was 100 nanoseconds, which seemed to us like incredibly tiny. But now 100 nanoseconds is wow. But 100 nanoseconds, and so we'd issue another instruction every 100 nanoseconds, provided there was a functional unit available that wasn't doing it. Well, in the loop for a merge sort, you have to do a comparison of two numbers, and then if depending on which is bigger, you increase I by 1 or J by 1, and then you always increase K by 1, and then you output the smaller of the two from XI and YJ into ZK. All right, so the 17 instructions, one of them's got to be comparisons, one's got to be increase I by 1. You can start figuring out. But then there's an interlac but you also have to test whether I has gotten to the end of it of the data, and J and K. And so these instructions are mounting up, and besides, if you're waiting to do a comparison of the value of I, it gets sticky. So finally worked out how I could use a double precision floating point divide to compare the sign of I and J. That unit wasn't doing anything because we weren't dividing, but that was something I could issue that instruction because it wasn't conflicting with anything else in the pipeline, and so we could use the divide instruction to check on the sign of things, which was enough to be a branch on the for getting out of the loop, and so getting that sort routine down to 17. Instructions was a good 3-day project, and it made the sort routine 4 times faster. But actually, then we got it out on the floor, and it only ran 2 times faster. But I knew that it was supposed to run 4 times faster. So then we found that there was a bug in the software for the disk that we had everything had been running at half speed all year. And we had never known that our disk was going at half speed. It was my point is that looking at things in the small and tuning things carefully can have a payoff even on big machines.
Would you say today that readability and maintainability of programs has become more important than parsimony?
That's absolutely true. The readability thing and maintainability and so on. Yeah, But my shtick on that is literate programming, and I don't carry readability to the point where it says that the computer should be able to understand what it's doing. I figure you should be able to explain to a competent programmer what it's doing, but you shouldn't say, well, I'm not going to use any algorithm that's not taught in first year because some maintainer might not understand the algorithm. There's this algorithm that they now teach the first year students called the Knuth Morris-Pratt algorithm. Well, Jim Morris thought of it before Juan and I did, but he put it into he put it into a server at Berkeley, but somebody looked at the code 4 months later and didn't understand it and ripped it out. So it wasn't maintainable, at that time, because he used a method that they said it doesn't make sense to me, and they took it out. So I don't believe that programs have to be readable by an idiot. But if there's any subtle thing going on, I think that has to be very well explained, and literate programming works very well for that. It says this is why. Don't do this because here's a bug that we worked very hard to find, and that stays with my program. So certainly, all these tricks that I was doing in those days, right now this summer I'm writing maybe, I don't know, 5-10 programs every week, and I'm emphasizing readability, maintainability in those programs much more than shoehornability.
That's good.
I was faced 2 days ago with a design that's similar, though. In a way, I'm trying to figure out a code for it. It's actually a way to do a diagram in my book, and it's a 2-level diagram. And I wanted to, and so the stuff on the top level conceals, or it can conceal things on the bottom level, but I designed a way so that I could paint a spot on the top level so that you could figure out in principle what was on the bottom level, but I had 20 different cases. And I had to find 20 different places to put the spot on the upper level and make them intuitive. And it turned, so again, it was very much, I started out and I said, well, how many slots do I need? Okay, 20. Well, So the eight obvious ones aren't going to be enough, then but it was very much this kind of a design where I was looking for some elegant mapping, and it happens when you're developing software. You want to have some codes that the code for one phase might be usable in another one, instead of having 2 arbitrary codes that don't fit together. All this training, I think, was useful.
Well, thank you. I think those were all the questions that we had, Don. If there's anything that we've missed that you'd like to say?
So to make an appointment, then to come and see what I have at home, because a lot of stuff that I have is one of a kind, but even if it's one of a kind, might not mean that it's valuable to history or not. Other things I have are just my own copy of things that do exist 100 places. And you've already digitized more than 100 of my collection, but still it's it might be more like 5% of the shelf space has been digitized, and then I've got I've got lots of other files too that I don't want. Let's not talk about. But these are, but this, the old stuff was stuff that I brought with me when I came to California, I went to Stanford in the end of the '60s, and that's all one. I changed my filing system then, and all of these come from that, and so I can best show it to you when I'm there, and then I have a computer index for everything.
Great. Well, we'll look forward to doing that.